Most people have never heard of gallium. That's the strange part. You can spend your entire life surrounded by technologies that depend on it and never encounter the word once. Yet somewhere inside your phone, inside advanced radar systems, inside satellites orbiting above Earth, and increasingly inside AI infrastructure, there is a good chance gallium, or a compound built from it, is doing important work. And for years, America was comfortable with that reality. Because the assumption was simple. The United States led the most advanced semiconductor companies. It dominated chip design. It controlled key intellectual property. Its allies controlled crucial manufacturing equipment. The higher you climbed the technology stack, the stronger America's position appeared. There was just one problem. Somebody forgot to look down. Because while governments were arguing about processors, fabrication plants, and export controls, China spent years strengthening its position in something much less glamorous: raw materials, the ingredients. The stuff that exists before a semiconductor becomes a semiconductor. That distinction matters more than it sounds. A cutting-edge chip is useless if critical materials don't reach the factory. A radar system doesn't care how sophisticated the design is if key compounds become scarce. And this is where the story gets interesting. According to the United States Geological Survey, China has long accounted for the overwhelming majority of global gallium production and refining capacity. In some years, the share has been so large that the rest of the world looked less like a competing industry and more like a footnote. Nobody panicked. Why would they? Gallium wasn't viewed as a geopolitical weapon. It was simply another industrial material moving quietly through global supply chains. Then the semiconductor war intensified. Washington introduced increasingly aggressive export restrictions targeting advanced chips and manufacturing technology. Beijing watched carefully. And eventually, China responded. Not with fighter jets, not with sanctions of its own design, with raw materials. That should have been a wake-up call, because it exposed something that many policymakers had spent years overlooking. Technological dominance and supply chain dominance are not the same thing. You can lead in one and still be vulnerable in the other. Actually, vulnerability is probably too soft a word. Dependency might be more accurate. Think about it this way. Imagine owning the world's most advanced bakery. You have the best ovens, the best recipes, and the best chefs. Then one morning, you discover someone else controls most of the flour. Suddenly, the conversation changes. Not because you've become less capable, because capability without inputs has limits. This is where compound semiconductors enter the story. Unlike traditional silicon chips, compound semiconductors use combinations of materials such as gallium arsenide and gallium nitride. These materials can handle higher frequencies, greater power levels, and harsher environments than conventional silicon. They're increasingly important for 5G networks, military radar systems, satellite communications, electric vehicles, advanced defense technologies, and perhaps most importantly, they're becoming critical components in sectors governments increasingly classify as strategic. Notice what happened there. A material that once sounded obscure suddenly connects to national security. That's rarely an accident. There's another detail worth paying attention to. China didn't build this position overnight. The groundwork stretches back years through investments in mining, refining, processing, and industrial policy. Much of it happened while Western governments focused on other priorities. The result is a situation that feels almost backward. America retains enormous advantages in technology. China controls significant leverage in materials. Both sides understand this. Neither side likes it. Which brings us to the question that sits underneath the entire semiconductor conflict. What happens when the country leading the technology doesn't fully control the resources needed to build it? Because history suggests that question rarely stays theoretical for long, and the answer may determine much more than the future of chips. We'll come back to that. The temptation here is to treat gallium as a rare earth story. It isn't. In fact, That's one of the reasons so many people underestimated it. Rare earths receive attention because they're famous. Gallium rarely makes headlines because most people have never needed to think about it. Yet some of the most important technologies in the modern economy depend on compounds built from this material. Take gallium nitride, often shortened to GaN. If you followed defense technology, you've almost certainly encountered it indirectly. Modern radar systems increasingly rely on GaN-based components because they can operate at higher power levels while generating less heat. That's a deceptively important advantage. A radar that sees farther isn't just a better radar. It changes military planning. It changes air defense. It changes the confidence commanders have in what they can detect and what they might miss. The same material appears in telecommunications infrastructure, satellite systems, and increasingly in power electronics. That's the thing about compound semiconductors. They don't always attract the attention that AI processors or advanced CPUs do. They're usually hiding deeper in the supply chain, doing highly specialized jobs that most consumers never see, until they become difficult to obtain. Then everyone suddenly learns their names. History has a habit of working this way. The products people obsess over are often built on industries they barely notice. Oil wasn't interesting because it looked impressive. Oil mattered because everything else depended on it. Steel wasn't important because people admired steel. Steel mattered because railroads, ships, bridges, and factories depended on it. Raw materials tend to stay invisible until a shortage reveals their importance. Which brings us back to China's position. For years, Beijing pursued a strategy that many Western policymakers viewed as old-fashioned. While much of the developed world shifted attention toward software, services, and high-value intellectual property, China invested heavily across physical supply chains. Mining, refining, processing, industrial manufacturing. The approach wasn't always elegant. Sometimes it wasn't even profitable. But it created something valuable: control. Not absolute control. That's an important distinction. No country controls every aspect of a supply chain forever. What China built was leverage. And leverage becomes visible only when somebody needs what you have. A useful example comes from 2010. Following a diplomatic dispute with Japan, concerns emerged over China's rare earth exports. Whether one agrees with every interpretation of that episode or not, policymakers around the world received a reminder that resource concentration carries geopolitical implications. Many governments promised diversification afterward. Some progress happened, much less than people expected. Because diversification sounds simple until someone calculates the cost. Building a mine takes years. Building a refining industry can take even longer. Environmental approvals add delays. Workforce training adds delays. Infrastructure adds delays. Suddenly, a dependency that looked temporary starts lasting a decade. This is where I think many discussions about America's semiconductor strategy become incomplete. The common narrative focuses on advanced fabrication, the CHIPS Act, Taiwan, ASML, export controls. Those are all important, but if you zoom out, a semiconductor ecosystem resembles a pyramid. Advanced chip design sits near the top. Raw materials sit at the bottom. The bottom is less glamorous. It's also harder to ignore when something breaks. And that's exactly why China's restrictions on gallium exports attracted attention far beyond the mining sector. The immediate economic impact wasn't catastrophic. That wasn't the point. The message mattered. A country doesn't need to shut down an entire industry to demonstrate influence. Sometimes it only needs to remind everyone where certain dependencies exist. One dry observation here. Governments love talking about resilience right up until resilience requires spending money. Then enthusiasm becomes noticeably harder to find. Still, there is a counter-argument worth taking seriously. Some analysts believe China's leverage is overstated. They point out that alternative sources exist. New projects are being developed. The United States, Canada, Australia, and several allied nations are actively exploring ways to expand domestic production and processing capacity. They're right, to a degree. No resource monopoly lasts forever. The question isn't whether alternatives can emerge, it's how long that process takes. And that timeline matters because technology races don't pause while supply chains reorganize themselves. Remember the bakery example from earlier. Finding another flour supplier is possible. Finding one quickly is a different challenge altogether. We'll need that distinction for what comes next. Because the most interesting part of this story isn't China's control of gallium. It's what that control reveals about how technological power actually works. There's a number from the opening that I want to return to. Not the percentage of global gallium production, not the export restrictions. The assumption. The assumption that technological leadership automatically translates into supply chain security. Because once you start examining the semiconductor industry closely, that assumption begins to fall apart. Think about the smartphone in your pocket. The processor might be designed in California. The manufacturing equipment could come from the Netherlands. The memory chips might originate in South Korea. Assembly could happen in China or Vietnam. Critical materials may have passed through half a dozen countries before the final product even existed. Modern technology isn't a national achievement, it's a global chain. And chains are only as strong as their weakest link. This is where the story takes an unexpected turn. For years, many observers viewed China's position in raw materials as evidence of strength, and America's position in advanced technology as evidence of strength. Both were correct, but they were also asking the wrong question. The more important question is, which strength is easier to replace? At first glance, the answer seems obvious. Materials come from the ground. Technology comes from decades of research. Surely the technology is harder to replicate, and in many cases that's true. Yet reality is more complicated. Because raw materials aren't valuable merely because they exist. They're valuable because of the ecosystem built around them. Mining, refining, processing, transportation, environmental permitting, specialized engineering expertise, industrial know-how accumulated over years. A country can discover a new resource deposit tomorrow and still need a decade or more to build a functioning supply chain around it. That distinction often gets lost. The discussion becomes focused on reserves when the real bottleneck may be processing capacity. China understood this earlier than many competitors. According to various industry assessments, Beijing didn't just prioritize access to materials, it spent years building refining and processing capabilities that other countries often considered low margin and strategically uninteresting. The irony is almost painful. The parts of the supply chain many advanced economies were happiest to outsource are now some of the hardest to rebuild. And this brings us to the reversal in the story. Most people hear the phrase, China controls the raw materials, and imagine a position of overwhelming dominance. I don't. At least not entirely. Because China's control of gallium also reveals a vulnerability. If a country controls a critical resource, it usually benefits when global demand for that resource grows. But what happens if customers begin aggressively searching for alternatives? What happens when governments start subsidizing competing supply chains? What happens when industries redesign products to reduce dependency? Leverage can attract competition. Sometimes a lot of it. We've seen this before. Remember oil shocks in the 1970s? The immediate impact was significant, but the long-term result included energy diversification, efficiency improvements, and new production sources. Pressure changed behavior. That doesn't mean China's position is weak, far from it. The current advantage is real. The question is whether it remains equally powerful 10 years from now. And this is where I disagree with both extremes. One camp argues China has permanently cornered the market. The evidence doesn't support that. The other argues alternative suppliers will emerge quickly and solve the problem. The evidence doesn't support that either. My view sits somewhere in the middle. China possesses meaningful leverage today because it spent years building capabilities others neglected. At the same time, those capabilities are now attracting enormous attention from governments that suddenly realize how exposed they are. The result is a race against time. Can alternative supply chains emerge before strategic dependencies become even more entrenched? I'm not entirely sure. But I do know this. The semiconductor competition increasingly resembles a contest between two different forms of power. One side excels at designing the future. The other spent years securing the ingredients required to build it. Neither advantage is complete by itself. And that's why the final piece of this story isn't really about gallium at all. It's about what happens when two superpowers discover that each possesses leverage the other would rather not need. Let's answer the question hidden inside the title. Did China actually corner the raw material supply behind one of America's most important semiconductor sectors? In the short term, the answer is surprisingly close to yes. Not because China controls every mine, not because alternative sources don't exist, but because supply chains are measured by capability, not possibility. A government can announce a new mining project tomorrow, investors can approve funding next month, construction can begin next year. None of that creates immediate production. The semiconductor industry operates on timelines measured in decades. The mines, refineries, processing facilities, skilled engineers, transportation networks, and industrial ecosystems behind those materials take years to build and even longer to optimize. That's the reality Washington is confronting. And it's why this story matters far beyond gallium, because once you strip away the headlines, the real lesson has very little to do with a single mineral. It's about what happens when globalization creates dependencies that nobody notices until geopolitical tensions arrive. For almost 3 decades, the world optimized for efficiency. Companies searched for the cheapest supplier. Governments welcomed lower costs. Investors rewarded leaner operations. The system worked remarkably well, until politics entered the room. Then suddenly efficiency and resilience started looking like two different things. A supply chain that appears perfect during stable times can become uncomfortable during strategic competition. We're seeing that realization spread across multiple industries simultaneously. Semiconductors, battery materials, rare earth elements, solar manufacturing, critical minerals, advanced pharmaceuticals. The pattern keeps repeating. Countries are discovering that control over production matters. Control over processing matters. Control over transportation matters. And sometimes the least glamorous link in the chain becomes the most valuable. That's why I think the semiconductor story is entering a new phase. The first phase was about innovation. Who could invent the best technology? The second phase focused on manufacturing. Who could build it at scale? The phase we're entering now is about supply security. Who controls the inputs? Who controls the bottlenecks? Who controls the industrial foundations underneath everything else? Notice how different that conversation is. We're no longer talking only about the chip. We're talking about the ecosystem surrounding the chip. And ecosystems are much harder to dominate completely. This is where my own prediction comes in. I don't believe China will maintain the same level of leverage indefinitely. The incentives are simply too powerful. The United States, Japan, Australia, Canada, South Korea, and several European countries are already investing billions into supply chain diversification. Governments that once viewed these sectors as boring industrial activities suddenly see them as strategic assets. Money is moving. Projects are moving. Policy is moving. Eventually, some of those investments will succeed. But I also don't believe the West can rebuild these capabilities as quickly as many politicians suggest. Industrial capacity is not a software update. You can't download a refining industry. You can't install a mining ecosystem. You can't create decades of expertise through a press conference. Those capabilities have to be earned, and earning them takes time, which means the next 5 to 10 years may be defined by an uncomfortable reality. America will continue leading many of the world's most advanced technologies. China will continue holding significant influence across parts of the resource and processing chain. Both sides will spend enormous sums trying to reduce those dependencies. Neither side will fully succeed, at least not soon. That's why I think the future semiconductor battle won't produce a clear winner. Not in the way many people imagine. Instead, we'll likely see a gradual restructuring of global supply chains, with countries paying more, duplicating capabilities, and accepting lower efficiency in exchange for greater security. Expensive? Absolutely. Rational? Probably. Because nations tend to discover the value of resilience immediately after learning the cost of dependency. Remember that obscure material from the opening, the one most people had never heard of? Gallium. A few years ago, almost nobody outside specialized industries paid attention to it. Today, governments do. That's how strategic resources work. They remain invisible right up until the moment they don't. And somewhere in a ministry office, a corporate boardroom, or a semiconductor laboratory, somebody is probably studying the next bottleneck already. Because in technology, the biggest advantage often isn't controlling the product everyone wants. It's controlling the ingredient everyone forgot to notice. If you enjoyed this deep dive, stick around for the next one. The most important stories in technology are usually hiding several layers below the headlines, and that's exactly where we're headed next.